In a lot of ways, gravity is something we've been focused on for a very long time. In fact, one of the first labs we did in this class is we measured the acceleration of gravity. I had people take an object, throw it in the air, video themselves doing it, and then using video analysis to figure out how the object accelerates throughout that flight. So those experiments, which humans have been doing for a very long time, yield an acceleration due to gravity of 9.8 meters per second squared. And we've used that to solve tons of problems. What we haven't really talked about is where does it come from? And I think now that we're starting to study Newton's law of universal gravitation, it's pretty clear that this has to do with the force of gravity between the object and the Earth. And furthermore, that if we weren't talking about the Earth, if we were talking about something else, like say Mars, that the acceleration of gravity would probably be different. So really the point in this lesson is going to be try to figure out, why is the acceleration of gravity on Earth 9.8? Is the acceleration of gravity indicative of something else, something more general about the planet? And how could we calculate the acceleration of gravity on other worlds? So that's where we're going. So we're now becoming familiar with this new fairly complex equation for the force of gravity. It's important not to forget that using sigma F equals ma and a free body diagram of something just falling under the force of gravity, we came up with a simpler version. We called the acceleration of gravity little g. So if these both help you calculate the force of gravity, your weight, at least for something in a certain location, they must be equal to each other. So in other words, the mass of an object times the acceleration of gravity must be equal to the universal gravitational constant times the mass of that object times the mass of the planet divided by the distance between the planet and the object, which in general is going to be the radius of the planet, because anything on the surface is so small compared to the radius. So we end up with that. So there's one thing I suspect is pretty obvious, that when we set these equal, we have the mass of the individual object, whether it's this angry bird or anything else, that's on both sides. So we should just be able to cancel it. And that leaves us with a very simple equation for little g. The acceleration of gravity is the universal gravitational constant times the mass of the planet divided by the square radius of the planet. This should help us calculate 9.8 if we know how mass of the planet is and what its radius is. So I've put these values here for several celestial bodies, the Earth, and we better get 9.8 when we plug that in, if this is true, Jupiter and Pluto. So let's go ahead and solve for what little g should be using the Earth's values, hopefully getting 9.8. We'll do that for Jupiter and Pluto, and then we'll discuss a little bit more about what little g is, why the acceleration of gravity is important. So full disclosure, one of the things that can be frustrating for students about this unit is a lot of your success depends on how well you know how to use your calculator. So I'm using a traditional scientific calculator on my phone. You're welcome to use a TI graphing calculator or really anything you want that does scientific notation. But you got to be aware that these are different for most devices. So you really have to learn yours. So I'll show you the traditional scientific calculator, and then you figure out how to use whatever you're using. So the acceleration of gravity for Earth is the universal gravitational constant, which is 6.67 times 10 to the minus 11 times the mass of Earth divided by the radius of Earth. So let's plug that into the calculator and make sure we know how to do it. So easiest way, I think, for me 6.67 exp11 negative times 5.98 exp24. I get an answer. Rather than dealing with the inverse and then the square, which can sometimes cause order of operations issue, I'm just going to divide by the radius twice. 6370000 divided by 6370000. 9.83. I'm pretty happy with that. So let's do it now for Jupiter and for Pluto, and we'll see how these values are different. So obviously we see a much larger value for the acceleration of gravity for Jupiter and a much smaller one for Pluto. So objects brought to near the surface of these planets, Jupiter doesn't really have a surface, but near its outer radius, they will experience accelerations like that. At this point, it's worth talking a little bit more about what it means for little g to have one value or another. I think it should be clear that given the choice between using this equation or using this one, it's a lot simpler to use this one. We don't always have the ability to use it because little g is not a universal constant. It's something that changes to different values wherever you go. But it's pretty useful because the calculations for each of these locations just depend on the planet and how far you are from the planet. So any object brought that same distance from Jupiter, whether it's here or here or here, is going to experience that same acceleration of gravity. And similarly for Pluto, any object brought near it, the same distance from the center, is going to experience that acceleration of gravity. So little g becomes a property of where you are. It's a property of location. So we used this equation at first. We found little g experimentally. We threw this thing up and down and saw it was about 9.8 on average. And then we were able to calculate the force of gravity for any objects. We can do the same with this equation. We can figure out what the acceleration of gravity should be at a certain location. And that will be true for any object there, not just the object that we're studying. So let's take a couple examples of where this has been useful in the past. The idea of going to a different place in space, we've seen this already. It started with Isaac Newton when he used the motion of the moon around the Earth to figure out what the acceleration of gravity must be at this distance from the Earth. He wasn't talking about going to the moon. He was talking about going this far from the Earth, which is where the moon just happened to be. We could look at the moon's circular motion and we could figure out that the acceleration of gravity for anything out there was 0.00278. So little g is not just the acceleration of gravity, we call it the gravitational field. And that's a measure of how strong gravitational effects are in a certain location. We could do this ahead of time for the moon. And because the moon has a relatively small acceleration of gravity, we know that every object on the moon, if g is smaller than 9.8, every object on the moon is going to have a much smaller weight. And that's why things that we use on the moon, like say the car that was designed for the Apollo program, and here's a NASA photo of it, can be built really lightly. These wheels are made of kind of a mesh, which if you tried to ride on it on Earth, you would crush it right away. This was loaded up with heavy astronauts and big spacesuits and loaded up with rocks, and it was able to get over the moon without crushing. Comparable vehicle used to train them on Earth had to be much heavier built. So here's a NASA photo of the Earth version of it. And you can see it has regular car parts holding it up. So every object on Earth is going to have more weight than every object on the moon. So if we just figure out what the gravitational field of the moon is, we can easily calculate the weight by multiplying that number by whatever mass. So this equation is not just valid for Earth. It's valid for everywhere, as long as we either find what little g is experimentally, like Newton did using the moon, or we did using the Angry Bird, or if we calculate it using this equation and the mass of the planet and the radius of the planet.